Hi, this is TheoryStation and I'm John Duggan. This program is called Rational Choice Modeling. The series that we're in is the Basic Formal Theory Toolkit, and this is installment 11 in the series. So in this installment, I'm just going to pick up where I left off. So we're still talking about the multidimensional policy choice model. And here, multi just means two, to think, to keep things simple. So last time I described the policy space as just R2, it's the Cartesian plane. And we talked about Euclidean preferences and how you can represent those with a quadratic utility function. And that quadratic utility function was basically, it's -1 times the squared distance between a policy and the ideal point of this decision maker. Okay, so if I write that out fully, using the coordinates of our policy and the ideal point, it looks like that. And I talked about, well, you can graph this or try to graph it in 3 dimensions, but really it's easier to look at a picture of indifference curves. If this is the ideal point, then the indifference curves are just perfect circles around that point. Close enough. And now in this installment, I want to push this in a couple directions. So to begin with, let's add another decision maker. You can think about this. They could both be politicians or voters. It doesn't really matter at this point because I'm just thinking about preferences. So let's have a second person who has an ideal point. Let's say R. So our first person has Euclidean preferences defined like this. And our second person will have, again, Euclidean preferences with quadratic utility, and we'll define that person's utility function in the same way, but using the appropriate ideal point. So all right, so if in this picture, maybe this ideal point is person 1's ideal point, that's P, and person 2 has another ideal point, let's say R right here. And I can draw indifference curves for the second person as well. And they're going to be, again, concentric circles, but now centered at R. Okay, so that's simple enough to do, to put 2 people into this model. So now what I want to do is I want to introduce a super important concept in political economy, in economics and political science. It's the idea of Pareto optimality. Okay, so maybe you've heard this term. An equivalent term that's used, Pareto, is Pareto efficiency. And what this is it's a property of policies. That is, a policy can have this property or not, okay? If it has the property of Pareto optimality, we say it's Pareto optimal or Pareto efficient. So we'll say that a policy is Pareto optimal if there's no way to make one person better off without hurting someone else. Okay, so let's write this out formally. So we'll say X is Pareto optimal if for all Y, I'll just define it in the context of this simple two-person model. So I'm going to use two different conditions here. The first is if person 1 is better off with Y, so they get a higher utility, then person 2 must be worse off with Y. And then there's just kind of a symmetric version of this. If person 2 is better off with Y, then person 1 must be worse off. Okay, so right, so X is Pareto optimal if there's no way to change it that makes one person strictly better off and the other person at least as well off as they were before. Okay, so in terms of this picture, what does Pareto optimality mean? Well, first let me pick an X that's not Pareto optimal, this X here. So I'll just do this in red. So let's pick this X here. So it's a certain distance from our first decision maker. It's a certain distance from the second. Is there a way to make both people better off? Well, you could just imagine moving in a little bit, and this policy Y here is actually closer to both of these guys. So they both have a higher utility from Y. So that means that they're both strictly better off, and that means that X is not Pareto optimal. Okay. All right, so that's what it means to not be Pareto optimal. What would a Pareto optimal policy look like in this model? Well, let's just go down here. I'll try drawing these circles again. Here's our policy space. There's our first decision maker's ideal point, and here's our second person's ideal point. And here I've drawn two indifference curves around those ideal points. And notice I've drawn them so that they're just touching right here. And because these are perfect circles, this point, this X, this policy, is going to be on the line between those ideal points if I had drawn the ideal points in the right location. Let me just cheat a little bit. Okay, so X it's on this line between the two ideal points. And now let's ask, is there any way to make both these decision makers better off? Well, the answer is going to be no, and it's pretty easy to see. So to make person 1, this first guy, better off, we need to choose a policy that's inside this circle, that's closer to P. But obviously, any policy that's in that circle, so it has a higher utility for person 1 here, well, that's going to be outside the circle for our second guy. It's going to be further from R, and that guy's going to be worse off. So there's no way to make, and symmetric argument would work There's no way to make either person better off without hurting the other. So that means that this x here is Pareto optimal. And it should be pretty clear that argument would apply to any policies on that line between the two ideal points, including the ideal points. Okay. So that line segment, that will consist of Pareto optimal policies. Is there anything else that's Pareto optimal? Well, just thinking back to the previous picture, it should be pretty clear that it's not possible to find any other Pareto optimal policies. If we take something like, let's take y here. So it's not on that line between the ideal points. I can, well, if I draw the indifference curve for the other guy, that's going to be on this circle, center to P. And it's pretty clear that I can make both these guys better off than they are at Y. I can change this policy by just moving into this lens that I've formed here, okay? This lens is a kind of an important idea because whenever you have two indifference curves crossing if you have two people and their indifference curves cross and form a lens like this, that means that you can move into the lens, and that means you're going to be able to find a policy that has a higher utility for both guys. In this case, if I move from Y to this Z, let's say, Z is closer to P for the first guy, it's closer to R for the second guy. They're both strictly better off. So because, well, anyway, in short, there are no Pareto optimal policies that are off that line. And so this really consists of all Pareto optimal policies. Okay. Why is Pareto optimality a big deal? Well, it's used as a normative criterion to understand, well, one use of it is to understand in a positive analysis what the normative properties are of the outcomes that you're predicting. Sometimes interaction will lead to outcomes that are not Pareto optimal. That's clearly bad. You don't have to really adopt any specific kind of moral or welfare criterion. If you can make everyone better off without hurting anyone else, right? If you can make everyone better off, then clearly the outcome you're getting is not good, no matter what kind of sort of welfare principle that you're using. So it's used as a way of kind of measuring the normative value of the outcomes that we're seeing. And it's also used in a normative way. Like sometimes, if you're in a normative analysis, if you're trying to recommend certain choices or policies, you'll always want to recommend something that's Pareto optimal. And that can have pretty strong restrictions. In this model, Pareto optimality rules out the entire policy space except for this line segment. So Pareto optimality is extremely restrictive in a sense, okay? It really, if we impose Pareto optimality, we reduce this whole two-dimensional space to a one-dimensional segment. I should say, though, that it's not completely restrictive because there is still a whole range of Pareto optimal policies. Some are closer to the first guy, closer to P, and some are closer to the second guy because they're close to R. And you can certainly see that these two decision makers, they would have a hard time, they might agree that we should choose something Pareto optimal, so on this line segment, but they would have a hard time agreeing on which policy should be chosen. I mean, the first guy clearly has a preference to choose things closer to P. The second guy clearly would want choices closer to R. So what we would say is that Pareto optimality is an efficiency criterion. Okay, it boils things down, but it doesn't answer this distributive question of, well, should we choose something better for one guy or better for the other? All right, so Pareto optimality is it's a huge idea, and it comes up in many different kinds of models. But before I move on from this model, in the next installment, I want to talk about some extensions of this. First of all, we haven't really talked about policy choice here. We've really been talking about policies and preferences, but I want to think about a model of the status quo, but in this two-dimensional setting instead of the one-dimensional model. And I want to then, see what kinds of outcomes are implied by the optimality principle, and then compare those to this Pareto optimality criterion. And then I want to talk just a little bit about what we call non-Euclidean preferences. I'm just using circular indifference curves here, but that's really just for simplicity. So that's what's coming up in the next installment.